Finding the domain of the composition of two functions. Let's let f of x and g of x be two functions, and we're going to actually explore the domain of f of g of x. Now formally, the domain of f of g of x is the set of all x in the domain of g such that g of x is in the domain of f. And I have what written down here because that's pretty much the look on my student's face when I state that in class. So let me go ahead and try to illustrate this formal statement with a picture. So first of all, f composed with g of x means we are going to evaluate f at g of x. Alright, so if we were to draw a picture or a diagram with our function boxes and what's happening here, we're going to start with x values and we're going to plug them into our g function. Okay? So this is our starting point. So in order to proceed, it has to first and foremost be in the domain of g. We can't even get it into g if it's not in the domain of g. Alright, what comes out of the g box are our g of x values. Okay? So x goes in, g does its thing, and out shoots g of x. Alright? Now, our next step is to take these outputs and put them in to f. So f is going to evaluate the g of x. Alright? So what goes in here has to be in the domain of f. Alright? So we start with x. So we have to first and foremost choose values only that can go in g. And those values will produce g of x's that have to go in f. So we have to trim down our original values so that the ones that come out, the g of x's that come out, are legal to go into f. Because out comes my f of g of x. Alright, so that's our checkpoint here. Okay, and as always, everything is better illustrated with a real-life example. So let's go ahead and look at a particular example where we can see if we can determine that. We're going to let f of x be equal to the square root of x minus 2. And let's let g of x be equal to 2x plus 4. Okay, so again, let's draw little boxes here. So I plug in an x, g operates on it, and out comes 2x plus 4. That's what g does to x values. Okay, and so let's talk about what can go into g. Well, since g is a polynomial function, 2x plus 4, we know that the domain is all real numbers. We can put any number into our g box, and out will come 2x plus 4s. So it's 2x plus 4s that are going to go into my f box. Okay? So what comes out here is the square root of my 2x plus 4s minus 2. Right? That goes in place of my x value. And that's what's confusing about the composition of function. The x here in our f function, once we compose it with g, really represents g of x. Okay? So it's the g of x's that are getting plugged in to our function. So we see that the f is a radical function, and it does have some restrictions. We need only x values such that this expression in here is greater than or equal to 0. So we're really looking at 2x plus 4 minus 2 needs to be greater than or equal to 0. Okay, what's under that radical needs to be greater than or equal to 0. And so now we're going to solve for the x that makes that true. 2x plus 2 is greater than or equal to 0. 2x is greater than negative 2. X is greater than or equal to negative 1. Okay, so we are now talking about our original x values, which we have no restriction on what goes into g, but we do have restrictions on what goes into f. So we pared down our original domain into ones that gave us values that once we plugged into f were legal. So x greater than or equal to negative 1 is the domain of the composition of this function. That is, it is the set of all x in the domain of g such that g of x is in the domain of f.